Welcome to The Explainer. Today, we are going to dive into the biggest, emptiest places you can possibly imagine in the entire universe. We're talking about cosmic voids. And believe it or not, these vast regions of nothingness are actually forcing us to rethink, well, pretty much everything we thought we knew about the cosmos.
So, picture this. It's 1981. A team of astronomers is painstakingly mapping out the universe in 3D. They're expecting, a nice, even sprinkle of galaxies everywhere. But what they found was, well, not what they expected. Instead, they found something shocking. Or, more accurately, they found a whole lot of nothing, right where there should have been something.
And we're not talking about a little gap here. This thing was absolutely colossal. A void in the constellation Bootes, stretching, get this, 330 million light years across. It's almost impossible to wrap your head around that number. I mean, to put it into perspective, our entire Milky Way galaxy is only about 100,000 light years wide. This void is just mind-bogglingly huge. Yeah, so an emptiness that big, that profound, it quickly got a nickname that was just perfect. The Great Nothing. And trust me, when you see the numbers, you'll understand exactly why. Okay, so in a chunk of space that enormous, scientists figured, hey, there should be thousands of galaxies in there. But what did they actually find? 60. Just 60. And to make it even weirder, those few galaxies weren't even spread out. They were all clustered together in this one lonely, tube-like shape. So you have to ask, what is this thing? Is it a giant black hole that just gobbled everything up? Or maybe some massive dark cloud that's blocking our view? Nope, it's neither of those. The Boyuta's void is something much more fundamental. It's a real, genuine part of how the universe is built. And to really get what that means, how the universe is built, we have to zoom out. I mean, way, way out. We need to look at the biggest picture imaginable, what scientists call the cosmic web. Okay, so forget thinking of the universe as just a smooth, even spread of stars and galaxies. That's not how it works at all. A better way to picture it is like a giant cosmic foam. Like soap bubbles? It's made of these dense strands or filaments of galaxies, and in between all those filaments are these huge, empty bubbles. Those are the cosmic voids. Now, this incredible structure didn't just pop into existence. It took billions of years to form. It all started back in the very early universe. Tiny little quantum fluctuations, think of them as tiny wobbles, created spots that were just a smidgen denser than the areas around them. And then gravity did its thing. Over eons, it pulled more and more matter into those denser spots. As the universe expanded, these clumps of matter got stretched out into the long, stringy filaments we see today. And what was left behind? You guessed it, these enormous empty voids. And this is where it gets really wild. Take a look at this. It shows just how much of the universe is, well, empty. All the stuff we actually see, all the galaxies, the stars, the planets, everything, it's all crammed into just 20% of the volume of the universe. So what's the other 80%? It's the voids. The universe is, quite literally, mostly nothing. But here's the twist. It turns out that not all of this nothing is created equal. You see, the neighborhood a void finds itself in can totally change its entire character. And that leads scientists to a really important question. Does a void's cosmic neighborhood, what's around it, actually change its fundamental properties? And the answer, it turns out, is a big yes. So first up, you've got what are called R-type voids. A good way to think about these is like isolated bubbles floating in a really sparse part of the cosmic ocean. They're just kind of expanding out on their own. And then, on the other hand, you have S-type voids. These are completely different. They're basically squished in between the super-dense, galaxy-rich superhighways of the universe. They're surrounded and squeezed by all this heavy stuff. Okay, so this whole R-type versus S-type thing, it's not just a neat little classification. It's actually a huge deal because it's helping us solve a really deep mystery in cosmology called galaxy bias. So what is galaxy bias? Well, here's the thing. The galaxies we can see with our telescopes, they aren't a perfect map of all the matter in the universe. A lot of matter is invisible dark matter. Galaxy bias is basically just a measure of how well the visible galaxies trace that invisible map of dark matter. It tells us how lopsided the relationship is. So that brings us to the key question, right? Does this bias, this mismatch, change depending on what kind of void a galaxy lives in? Is it different for a galaxy in a chill, expanding R-type void compared to one in a crowded, squeezed S-type void? And the answer is a definitive yes. It absolutely does. Simulations show that galaxies inside those squeezed S-type voids are way more biased tracers of the matter around them than the ones in the R-type voids. The neighborhood makes all the difference. And what's really fascinating here is that this isn't because the galaxies are bigger or smaller. It has nothing to do with their mass. It's purely about their large-scale environment. This is what's known as a secondary bias effect. It's the cosmic address that's changing their behavior, not the galaxies themselves. So, why should we care about all this? What's the big deal? Well, because these subtle differences hiding inside all this great nothing could actually force us to rewrite the rules of the entire universe.
You see, our standard model of cosmology, the one that's been so successful for decades, is built on one really big assumption, that if you zoom out far enough, the universe is basically smooth and uniform. But as we've just seen, the cosmic web is, well, it's anything but smooth. It's lumpy and foamy. And that makes these voids an incredible cosmic laboratory. By studying these massive empty patches, we can test some of the biggest ideas in physics, things like dark energy or even alternative theories of gravity. And maybe, just maybe, they can help us solve one of the biggest headaches in cosmology right now, the Hubble tension, which is this huge disagreement over how fast the universe is actually expanding. In fact, some scientists are now thinking that if we just properly account for this foamy structure, the fact that voids are expanding differently than the dense falls, we might be able to solve these huge problems. We might not need some crazy new physics after all. The answer could have been hiding in the emptiness this whole time. Which leaves us with one last really provocative thought. What if the key to understanding everything, the expansion of the universe, the nature of gravity, all of it, isn't found in the bright, dense, crowded places? What if, by studying the great nothing, we actually end up finding the richest answers of all?